Hello, my name is Satyam Agarwal and I will talk about explosive events on the Sun. An explosive event like a flare can release lots of energy and can cause geomagnetic storms on Earth. Therefore, it is crucial to understand them. Flares vary in their strength and on the basis of soft X-ray emission they are divided into BCM and X class, where X class flares are the strongest. The released energy comes from the magnetic field of the Sun, which you will notice to be very complex as compared to that of a bar magnet and the Earth. This energy is released by the magnetic reconnection process, which can be easily understood in two dimensions. When two anti-parallel field lines, example AB and CD, come very close, they reconnect, which changes their connection leading to field lines AC and BD. Also, from Ampere's law, very close or small length implies large current density J, which produces significant ohmic heating during these events. The shown geometry is called a X-type null point, and null point is the location where all components of the magnetic field are zero. In three dimensions, we have a 3D null point and a hyperbolic flux tube or HFT. In HFT, just remember that a X-type region exists, similar to the X-type null point in 2D. In my thesis work, I explored explosive events from the perspective of self-organization and attempted to address the existence of flares with different strengths. Self-organization refers to spontaneous generation of ordered state which is nearly independent of the initial conditions. To understand, two boxes with a partition contain different number of blue and red balls on each side. On removing the partition, the final state is the same. Realistic examples include coronal loops on the Sun and galaxies in the universe, which form spontaneously and are ordered structures. To study flare dynamics, MSD simulations are needed. Then, initial conditions require specification of magnetic field and plasma flow. Since magnetic field of the Sun is usually measured on the photosphere only, extrapolation models are used to construct the three-dimensional solar magnetic field. We use the non-force-free and non-linear force-free models to devise three initial conditions as shown. In two cases, there is no plasma flow, while in the third case, a perturbative flow is added. We carried out simulations to solve the MSD equations and looked at the results relating to magnetic reconnection. We found the changes in field line connection to be nearly similar at a 3D null point, which was obtained in both the models. Here P and N refer to positive and negative magnetic polarities. The primes are for the NLFF model and open refers to the open magnetic field lines. Also, you can see that dissipated magnetic energy is similar in all the cases. The key conclusion is that the results are nearly independent of initial conditions and both the models can be used to study flare dynamics. We also investigated flares of different energy classes, namely a B, C and M class flare. Using non-force-free extrapolation, we found a 3D null point for B and C class and a HFT for M class. Then, using extent of these geometries in x and y direction, namely nx and ny, height of the null point or x region of HFT, namely h, and nearby magnetic field strength, we calculated a quantity called Rx. Then we found that the ratios as shown in the table were nearly equal to ratios calculated from the measured intensity from the ghost satellite. This means that energy released in flares is related to the magnetic field and may be predicted by analyzing the reconnection site. However, further statistical studies are needed in this direction to validate Rx for space weather applications. That's all from my side and I leave you with the summary of my thesis. Thank you.